Hello. So we ended our last lecture here, where we are trying to study how to apply the Neumann boundary conditions to the problem that we're given. Okay. So I will just go back. This is the problem. It's a Laplace equation on this domain. We looked at how you can apply the discretized equation to nodes 4, 5, and 6. Okay, and I want to make a point here that when you look at the final equations that we get, note that this corner point here does not even appear in the equations. Okay, as well as this one. That's because, for instance, when we are here, we are using this, and that, and so this does not appear. When we are here, we are applying this and this, and that. So these points do not appear in the equations. I just want to make that point before we continue. Okay, so the way you apply the Neumann boundary conditions is that you can apply the central difference formula to the first derivative here. The phi dy would be equal to, you can just take, for instance, across 1, you can take the value there minus a fictitious point below, so that phi south will be something here that we do not know. That is the idea. And when we are here, we're going to take this minus another fictitious point here to give us whatever is there. And so that is the idea. So the phi dy at each node 1, 2, 3, we want to use this. The phi dy is equal to phi n minus phi s prime because it's a fictitious point, divided by 2 delta x. But this is equal to 0. So I can just multiply through by this, and I have phi s prime is equal to phi n. Okay, I mean, if the phi dy was equal to some function, I mean, you can still use the same approach. Okay, and so what you do is that you then apply this to the formula, right? The compass notation formula for the discretized equations, so that wherever you see phi s, right, you replace it with phi n, and so the equation becomes this. Okay, so if you look at our equation here, we have this. Because we are applying the Neumann boundary conditions, phi s becomes phi n, so this is phi n. So phi n minus phi n is negative 2 phi n, and so you end up with minus 2 phi n here. Okay, and the other ones remain the same. So now you can now apply this formula 14 to each of nodes 1, 2, and 3, and that will give you another set of 3 equations. Okay, already we have 3. So when you do that, applying 14 to nodes 1, 2, 3, you end up with these 3 equations. You get system 15, and so you have 3 equations from the internal nodes, 3 equations from the Neumann boundary condition. That gives you 6 equations and 6 unknowns, right? Nodes 1 to 6, and so you can group them and put them in the form of a matrix. Okay. Again, I've made this point before that if you look at the equations, system 13 and 15, the corner points are missing, so they don't really appear in the equations. So you don't really need to worry about them in this case. So combining 13 and 15, you can put them together in the form of a matrix as we've done before. Okay, and that gives you this. Later we see that you don't necessarily have to put it in a matrix form like this. We'll see that for the iterative schemes, you can actually solve the equations iteratively, each equation. Okay, we'll come to that later on. But for now, you can combine them. The first 3 rows of the coefficient matrix here, all right, are taken from the coefficient matrix of 15. So these guys. These first 3 equations, they are the ones that occupy the first 3 rows here, and then the next 3 rows you get those from the system of equations from the internal ones. So 1, 2, 3, these ones, they occupy the last 3 rows. These guys. Okay. So so now we have system of 6 equations and 6 unknowns in the matrix, and then you can solve it as before, and then you have your solution to it. Okay, so that is how you deal with Neumann boundary conditions. Good. So now if you go back to this, note how this matrix is very sparse, right? It is not like a tri-diagonal. You see, you don't have ones all here. You have zeros that are scattered all over the place. So it's quite sparse. Because it's sparse, if you have a large matrix, it's not efficient to solve it directly using direct methods like the Gaussian elimination. Okay, it's very expensive numerically to do that. So what we're going to do is actually develop so-called iterative methods. So that is the Jacobi and Gaussian methods to solving them. So that is what we're doing next. Okay. So let's move straight to iterative solutions of these elliptic equations. So the idea for this so-called iterative method is basically we start from here. So given an algebraic system of equations like this, how can we solve it efficiently, iteratively? In other words, solve one equation at a time till you get a final thing. All right. So the idea is that the coefficient matrix here, you rewrite it to be a sum of the lower triangular matrix, the red entries here, plus the diagonal elements, plus the upper triangular elements. Okay, so A is split into that form. So A is written as L plus D plus U. L is the lower triangular, the diagonal, and the upper triangular matrices. Okay, then just plug this back into the equation AX equals B, and then you get that. Okay, so you can rewrite this and leave the diagonal elements on the left hand side and then the other ones on the right hand side, and then from here you can develop actually an iterative scheme. Okay, so you assume that you are given some initial vector x, say zeros, right? And then you solve for x, and then you go to another step where you plug in what you have already found into here, then solve for another x, and so on until you converge to some solution. Well, you specify some kind of a tolerance until the solution of your previous solution from your previous step. The difference between the solution of your previous step and your current step is say less than some tolerance, and then you can end the iteration there. Okay, so that is how these things develop. We'll do some examples to illustrate that. So the Jacobi method, from here, the Jacobi method says that if the inverse exists, right, then we can get an iterative scheme like this. So multiply through by the inverse, and then you get this. Okay, so you just let the right hand side values x to be the current ones, where you specify the initial one when r is 0, r is just some integers, right? R is 0. You specify this, and then solve for x r plus 1, and then you continue until you get a final solution. So that is the Jacobi method. All right. Well, actually, in my next video, I'll do an example of the Jacobi method, and then we'll move on to the other one, the Gauss-Seidel, which is an improvement over this one. Okay. So that is what we'll do next.